Welcome to the Explainer. If you're tackling the Cambridge IGCSE Physics 0625 syllabus, you already know that the glossary at the back of your textbook can feel like a massive, dense brick wall of text. But today, we're doing something completely different. We are taking that exact A to Z list and decoding it. We're going to transform all those disconnected terms into a logical, interconnected map of the universe, moving from the macro scales we can see all the way down to the micro scales we can't. Let's get right into it.
Here's our flight path for today's session. We'll kick things off with forces in motion, transition into energy transfer and work, check out the physics of waves, map out electricity and magnetism, and wrap up with atoms, radiation, and space.
Section 1. Forces and motion, the physical rules of the visible world. We're starting our journey on solid ground, looking at the foundational rules that dictate how everything around us moves, pushes, and pulls.
Now, examiners love to test you on this exact distinction, scalar versus vector. Think of a scalar as just a raw number. It has magnitude only, like I'm running 10 miles an hour. But a vector adds the absolutely crucial element of direction. It's saying I'm running 10 miles an hour due north. That single addition of direction changes how we calculate literally everything in physics. Oh, and hey, before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay, let's look at how that vector-scalar difference plays out in reality with mass versus weight. So many people mix these up. Mass is a scalar. It's just the sheer quantity of matter you're made of. It doesn't care where you are. Weight, on the other hand, is a vector. It's the actual gravitational force pulling down on that mass. Meaning, if you teleport it to the moon right now, your mass stays exactly the same, but your weight drops drastically because the moon's gravity is weaker.
And that brings us to the ultimate rule of how things behave, Newton's first law of motion. Essentially, objects are incredibly lazy. A stationary object will just sit there forever, and a moving object will keep gliding in a perfectly straight line at the exact same speed forever unless an external force forces it to change.
But in the real world, things get messy. What happens when multiple forces are yanking on an object at the same time? Enter the parallelogram law. It's this brilliant geometric trick. You just draw your two forces as the sides of a parallelogram, complete the shape, and boom, the diagonal line right through the middle gives you the exact resultant force. It tells you exactly where that object is going to go.
Section 2. Energy transfer and work. How work is done and conserved. So if forces are the pushes and pulls, energy is the underlying currency that pays for all that action. Nothing happens without it.
This right here is one of the most unbreakable laws in the entire universe, the principle of conservation of energy. You can't just magically summon energy out of thin air, and you can't destroy it into nothingness. You can only transfer it. Whether it's the chemical energy in the food you eat becoming kinetic energy when you run, the total amount of energy in the system is always perfectly conserved. Just look at this number on the screen, 3.6 million joules. A joule is the standard unit of energy, but it's super tiny. That massive 3.6 million figure is what just one single kilowatt hour equals. So next time you see your family's electricity bill, just remember you're burning through millions and millions of joules just to keep the lights on and the fridge cold. And since we can only transfer energy, where we get it from is a huge deal. The syllabus breaks this down into two clear camps: renewable sources like solar, wind, and geothermal, which replenish themselves naturally, and non-renewable sources like fossil fuels and nuclear fuels. Once we burn through those, they are gone for good.
Section 3. The physics of waves. Unveiling the invisible forces. Now we're stepping away from solid blocks and heavy fuels to look at how energy travels invisibly through space and matter. But hey, stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, let's look at the mechanics of waves. There are two main types you absolutely need to know. Transverse waves, like light or water ripples, vibrate perpendicularly to the direction they travel. They go up and down while moving forward. But longitudinal waves, like the sound of my voice right now, vibrate parallel to their travel. The particles physically pulse back and forth in the same direction the wave is moving. Now, waves don't always move at the same speed. When light passes from air into water or glass, it slows down. This sudden change in speed causes the wave to bend, a phenomenon we call refraction.
The refractive index is just the mathematical ratio of how much that wave's speed changes between the two materials. It's the exact reason a straw looks magically snapped in half when you drop it into a glass of water.
Section 4. Electricity and magnetism. Circuits and fields. Let's zoom in even closer and map out the invisible flows of electrons and the magnetic fields that are quite literally powering the device you're watching this on right now.
You've got to understand how we wire things up. In a series circuit, everything is in one single loop. If one light bulb blows out, the whole entire circuit dies because the path is broken. But parallel circuits? They are a total game changer. They connect components side by side so the current can split into different branches. That's why if a bulb burns out in your kitchen, your living room TV doesn't suddenly shut off.
Okay, this is literally a cheat code you can bring into the exam room with you. Fleming's left-hand motor rule. When a wire with current runs through a magnetic field, it gets pushed. To figure out which way, use your left hand. First finger points with the magnetic field. Second finger points with the current, and your thumb automatically points in the direction of the physical force, or thrust. It's a 3D physics calculator built right into your hand.
To make sense of all these invisible forces, we use three core quantities tied together by Ohm's law. Electric current, measured in amps, is the actual flow of the charge. Potential difference, measured in volts, is the push that makes that charge move. And resistance, measured in ohms, is how much the material fights back against that flow. So, we've covered the everyday mechanics and the electrical currents flowing through our walls. But as we head into the final stretch, we have to ask a massive question. What exactly is going on at the absolute extremes of our universe, the incredibly tiny and the mind-bogglingly huge? Section 5. Atoms, Radiation, and Space. From the quantum to the cosmic. This is it, the ultimate building blocks of matter and the unimaginable expanse of deep space.
Down at the microscopic level, matter is held together by a beautiful, delicate electrical balance. Inside the nucleus of an atom, you have protons carrying a +1 charge, sitting next to neutrons which have 0 charge. And zooming around the outside are the tiny electrons, carrying a perfect -1 charge. That exact counterweight of positive and negative is what keeps the atoms in your body from just flying apart. But nature likes to mix things up, creating isotopes. Take tritium, for instance. Regular hydrogen is just 1 proton. Simple. But tritium is an isotope of hydrogen that somehow packs 2 extra neutrons into its nucleus alongside that single proton. It's the same chemical element, but that extra mass makes it heavier, unique, and unstable.
And when unstable isotopes try to find balance, they emit radiation. The crazy thing is how predictable this decay is. We use a concept called half-life, which is the exact amount of time it takes for half of a radioactive sample to decay. It ticks down perfectly from 100% activity to 50, to 25, to 12.5. It's just perfect statistical clockwork.
Now, let's jump from the invisible atom to the edge of the cosmos with redshift. When we point our telescopes at distant galaxies, the light waves traveling toward us are actually getting stretched out into longer, redder wavelengths. This redshift is our definitive, literal proof that the universe is expanding, and everything out there is racing away from us at incredible speeds.
And there you have it. We just transformed a dry glossary into a living, breathing map of reality. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly explainer sessions. So here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here.